Welcome to this explainer. We're going to completely demystify some of the most notoriously tricky electrochemistry mechanics out there. We're going to arm you with the mental models you need to totally conquer galvanic and electrolytic cell problems. And honestly, more importantly, how to avoid those hidden traps that trip up so many of us. So if you've ever second-guessed a sign, a polarity, or whether a reaction is spontaneous, you are in exactly the right place. Our roadmap today is super focused. We've got 1. Galvanic cells and anodes. 2. Avoid the salt bridge trap. 3. Electrolytic cells and electroplating. 4. The rechargeable battery flip. And finally, number 5. Calculating cell EMF. Let's just jump right in. Section 1. Galvanic cells and anodes. We're starting things off with the classic spontaneous systems. Pause for a second and think about this classic exam trap. In a system like a Daniell cell, one that's spontaneously generating power, is the anode positive or is it negative? And chemically speaking, is it oxidizing or reducing? It sounds like basic stuff, right? But under pressure, man, it is incredibly easy to mix these up. The ultimate cheat code you want to remember here is the mnemonic N-ox. Oxidation always happens at the anode. It doesn't matter what kind of cell it is, this is a universal rule. So in our Daniell cell, that means the solid zinc electrode is actively oxidizing. It's dissolving into zinc 2+ ions and basically shedding 2 electrons in the process. And what's really cool is how this process totally dictates our polarity, because that oxidation is dropping electrons directly onto the surface of the zinc metal. It builds up this excess negative charge. That means the galvanic anode is negatively charged. It acts like a source, spontaneously shoving those electrons out through the circuit toward the electron-hungry positive cathode. Section 2. Avoid the salt trap. Let's look at how a perfectly good setup can just completely fail. Imagine you're building a galvanic cell. You've got your silver and silver ion half cell looking great, but for your salt bridge, you just randomly grab potassium chloride. What goes wrong chemically the second you introduce KCl to a silver system? The fatal consequence here is precipitation. It literally drops your cell voltage to absolute zero. As those chloride anions migrate out to balance the charge, they instantly react with the silver cations. This creates silver chloride, which is a solid, insoluble precipitate. It essentially clogs up the gel matrix and totally blocks ion diffusion. And with no ion flow, your circuit is completely dead. To bypass this trap entirely, you gotta respect the rules of solubility. Basically, avoid chloride if you're working with silver, lead, or mercury. Instead, you always want to use nitrate salts. Things like potassium nitrate or ammonium nitrate are the gold standard here, simply because all nitrates are fully water-soluble. They give you perfect ion flow with zero risk of clogging up your bridge. Section 3. Electrolytic cells and electroplating. Now we're going to flip the script. We're going from spontaneous cells to forced systems. Here, we're no longer generating power, we're consuming it. So ask yourself, if we literally have to use an external power source to force a non-spontaneous reaction to happen, what does that do to the Gibbs free energy, our delta G? And how does that external power flip the charge on the cathode? You're going to want to lock this brilliantly simple mnemonic in your brain. Panic. Positive anode, negative is cathode. Since this is non-spontaneous, delta G is greater than 0. We've got an external power supply actively forcing electrons onto the cathode. That influx makes the cathode electron-rich, and therefore negative. This actually perfectly illustrates industrial electroplating. Say you want to coat a steel spoon with pure copper. You have to connect that spoon to the negative cathode. Why? Well, because that's where the electrons are being forced, which reduces the copper ions in the solution into solid copper right onto the spoon. Your anode, meanwhile, is just a chunk of pure copper that oxidizes to keep the bath fully stocked with ions. Section 4. The rechargeable battery flip. Let's pull this out of the chemistry lab and into the smartphone that is probably sitting in your pocket right now. Think about the exact moment you plug your phone into the wall. We know it takes in power, obviously, but what chemically happens to the battery's operating state? Specifically, what happens to the electrode that was just acting as your anode while you were scrolling and texting? The whole identity of the battery completely flips. When you're discharging it using your phone, it's a spontaneous galvanic cell. Delta G is less than 0, and it's releasing current. But the absolute second you plug it in, it turns into a forced electrolytic cell. Delta G becomes greater than 0 as it eats up that wall power to force the current backward and regenerate your reactants.
Now, the really fascinating part about this current reversal is what happens physically. It's called the electrode swap. Because electrons are being shoved in the exact opposite direction, the sites of oxidation and reduction physically trade places. Literally, the electrode that was your anode when the battery was discharging actually becomes your cathode the moment it starts recharging. Pretty wild, right?
Section 5. Calculating cell EMF. Finally, let's quantify all this theory and calculate the standard reduction potential of a system. Let's set up a classic calculation. Say you're given two standard reduction potentials, zinc at negative 0.76 volts and silver at positive 0.80 volts. How do you properly calculate the total cell voltage for a spontaneous cell without making a fatal sign error? And from that same data, how do you instantly spot the strongest oxidizing agent? If you break this down into 3 logical steps, the math becomes totally foolproof. Step 1, the higher reduction potential is always your cathode, and the lower is your anode. Step 2, just take the potential of the cathode and subtract the potential of the anode. And step 3, that highest reduction potential, that points you directly to the strongest oxidizing agent. So, applying the formula from step 2, our cathode is silver at positive 0.80 volts. Our anode is zinc at negative 0.76 volts. Subtracting negative 0.76 from positive 0.80 gives us a spontaneous cell potential of positive 1.56 volts. Watch out for that double negative becoming a positive. It's a classic trap where people just drop points on exams, so always write it out carefully. And following through on step 3, we just look at the raw numbers. Because silver has the higher standard reduction potential at plus 0.80 volts, it has the strongest pull to accept electrons. It really wants to be reduced. And that makes silver the strongest oxidizing agent in this pair. So, having decoded these systems and navigated these traps in today's explainer, from dodging salt bridge precipitates to nailing the math of electromotive force, I want to leave you with this. What other everyday devices, maybe sitting in your home or your garage right now, are quietly flipping their anodes and cathodes right under your nose? Keep an eye out for the chemistry hiding in plain sight. Thanks for tuning in.